Today we're talking waves, and there's a lot of different kinds of waves, and to help explain a couple different kinds of waves, I have a Columbia wave machine, patented in 1905. You can tell this is real history here because when I talk about this kind of wave, it notes right over here that it's an example of ether waves, which don't really exist. We thought they did back in 1905, but they don't. So let's talk about the different kinds of waves. Well, a basic kind of wave is a wave that has particles in it. You have to have a wave, it has to have a medium usually. Usually you think it has a medium. And it goes through like this. And so each of these dots is not a wave in itself, but the energy passing through them is the wave. So each dot represents a particle, okay? And like maybe people in the bleachers at a football stadium, and if you all do the wave together, all right, nobody actually moves back and forth, but you all throw your hands up. That's called a transverse wave. So if I spin this, you can see that every single circle just moves up and down, but yet it looks as if the wave is moving forward. All right? That's a transverse wave, okay? Like a wave in a football stadium. There's another kind of wave, which is a sound wave. Sound waves happen when particles squish together to compress and get a loud note, and then, well, that's not right. When particles squish together and then expand, and that's the wave, all right? And the more they squish together, the louder the noise. That's called the amplitude, all right? And then how frequently those compressions come right after another would be the pitch, how high or low sounding. So here each dot, right? So you'll actually see the dots won't move up and down, but they'll move closer and further apart. So there you go. You can see that it starts here and they squish together and then it spreads out and then it squishes together. Each dot doesn't move, right? So the medium, like air, doesn't move that much from its initial spot when sound waves travel, but they move back and forth. So each little dot moves back and forth, and you get a sound wave moving through. Another kind of wave, you might hear of waves on water, is sort of a circular motion. Okay, the water, and on the top of the water, each individual molecule, well, you know, clumps of water on the top, is moving in a circle in order to make what you would see as a water wave. So here's an example of water waves. Right? So if you watch individual particles, they're moving in a circle. But yet the overall, what you look at, you see that it's an actual, it looks like there's a wave propagating through. All right? So once again, we have transverse waves, like the kind of wave you might get on a string or an instrument. We have longitudinal waves, which is like a sound wave. And we've got waves like you might find in water. Slinkies are a great toy because they can be used to display different properties of waves. The basic property of wave is, again, that sort of vibrating motion, moving up and down, right? The up and down motion, how high up and down it goes, is called its amplitude, whereas how fast it moves up and down might be its frequency. Okay, and so I have a giant slinky sprung out here, and we can show both transverse and longitudinal waves. Transverse are pretty easy. I'll just take my slinky and start moving it back and forth. And you can see I can create a standing wave, or I can make it look as if the waves are moving down the field. There you go. Transverse wave is that side-to-side motion. So longitudinal waves will be a compression wave, right? The particles move back and forth in the direction of motion. So if I pull back some of my spring here and let it go, you can see the wave go down and it'll come back. You can sometimes see it come back. So once again, you see the compression going forward like that. That's just like a sound wave. Sound waves are compression waves in the air. And now we have a great demonstration to show that. Talked about different kinds of waves, and remember, sound waves is a longitudinal wave, a wave that compresses and expands. So it's very hard to see sound waves, of course, because it's air just squishing and uncompressing and compressing back and forth again. So we have fire. And fire is going to help us see sound waves. What I've got is a long tube filled with natural gas, okay? And it's got gas in it. If I send a signal of sound in there, that'll cause the pressure in the gas to increase and decrease. And so we have this tube filled with gas, little holes in the top, and each hole has a flame in it. And so the higher the pressure at each hole, then the taller the flame. Okay, and so we'll be able to see sound waves, and we won't. We'll actually make a standing wave in the tube. Sound travels faster than it looks, but we'll get it bouncing back and forth and overlapping, so it looks like standing waves. So let's dim the lights and check it out. So what I'm going to do is turn on a sound machine or a little speaker here on one end, and it'll start sending a sound through the flames. All right, that's a very high-pitched sound, and so the waves should be very tightly packed together. So I'm going to lower it down so we have fewer waves. All right, now I'm going to turn up the amplitude so you can see the pressure stronger. There you go. You can actually see the waves. So there's two things that are going to modify our flames. Okay, how loud the sound is will get more compression. All right, and so we'll get higher flames, and the pitch and how high or low sounding the sound will be will give us more or fewer waves. Higher pitches, more waves. So here we go. We turned it on. We turn up the volume a little bit. You can see lots of little tiny waves. If I turn down the pitch, we get fewer waves. Just a few waves. Turn it back up, and if I turn the amplitude up higher, the volume up higher, bigger amplitude. Low pitched is few waves. High pitched is more waves. Lots of little tiny waves. There you go. Fire.